Hello, everyone. Today we're going to dive into the fascinating world of computer-aided design and drafting, commonly known as CADD. Let me explain what CADD really means in practice. When we talk about computer-aided design and drafting, we're referring to a sophisticated system that goes far beyond simple digital drawing. Imagine having a virtual workspace where every line you draw is precise to the millimeter, where you can experiment with different designs without wasting physical materials, and where you can visualize your ideas in both 2D and 3D. CADD integrates traditional drafting techniques with powerful computer capabilities, allowing us to create, modify, analyze, and optimize designs with unprecedented efficiency. Think of it as having a smart assistant that helps you perfect every aspect of your design while ensuring accuracy and consistency throughout the process. Let's explore why CADD has become absolutely essential in modern engineering. First, let's talk about precision. CADD allows us to create drawings with incredible accuracy, far beyond what we could achieve with traditional manual drafting. The efficiency aspect is remarkable. Tasks that might have taken days to complete by hand can now be done in hours or even minutes. When it comes to visualization, CADD is like having X-ray vision into your design. You can see it from every angle, in both 2D and 3D. The flexibility is amazing. Imagine being able to modify your entire design with just a few clicks instead of redrawing everything from scratch. Collaboration has been revolutionized. Teams across different locations can work on the same project simultaneously. And perhaps most importantly, CAD's ability to simulate and test designs before production saves enormous amounts of time and money by catching potential issues early in the design process. Now, let's examine the powerful features that make CADD such a versatile tool. Starting with drafting tools, these are your digital pencils and rulers, but with incredible precision. You can create perfect geometric shapes, add detailed annotations, and include precise measurements with just a few clicks. The modeling capabilities are truly remarkable. Imagine being able to take a flat drawing and transform it into a three-dimensional model that you can rotate, slice, and examine from any angle. The simulation and analysis features are like having a virtual testing laboratory. You can subject your design to various conditions to ensure it will perform as intended. Rendering capabilities allow you to create photorealistic images of your designs, perfect for presentations or marketing materials. And automation features help you save time by handling repetitive tasks automatically. Think of these features as your digital Swiss Army knife, each tool serving a specific purpose, but working together seamlessly. Understanding how to interact with CAD software is crucial for efficient design work. Let's break down the interface components. The user interface, or UI, is like your digital control center. The ribbon menu houses your most frequently used commands, similar to having your most important tools right at your fingertips. Toolbars provide quick access to common functions. Think of them as shortcuts to your favorite tools. The command line is your direct line of communication with the software, allowing you to input precise commands and dimensions. The Properties palette lets you fine-tune every aspect of your design elements. The Viewport is your main workspace, like an artist's canvas, but with the ability to show multiple views simultaneously. This multi-view capability is particularly useful when working on complex designs, as you can see your work from different angles at the same time. Let's explore more aspects of CAD software interfaces that make our design work efficient and organized. File management in CAD is like having a sophisticated digital filing cabinet. You can save your work in various formats like DWG or DXF, making it easy to share with others or use in different software. The plugins and extensions are particularly exciting. Think of them as special add-on tools that enhance your software's capabilities. For instance, if you're working on architectural designs, you can add specific tools for that purpose. And here's something really wonderful about CAD interfaces. They're customizable. Just like arranging your physical workspace to suit your needs, you can modify toolbars, create shortcuts, and set up your workflow exactly how you prefer it. This personalization helps you work more efficiently and comfortably. Now we're going to explore the diverse family of CAD software available to designers and engineers. Think of each CAD software as a specialized tool in your digital workshop. AutoCAD is like your versatile all-purpose tool, excellent for both 2D and 3D work across various fields. SolidWorks specializes in mechanical design. Imagine it as your mechanical engineering expert. CADD is the heavyweight champion, particularly beloved in aerospace and automotive industries for its comprehensive capabilities. Revit is your architectural specialist, particularly adept at building information modeling. Fusion 360 brings something special to the table, cloud-based collaboration, making it perfect for team projects. And SketchUp is like your friendly introduction to CAD, particularly popular among architects and interior designers for its user-friendly interface. Let's walk through the typical workflow in CAD software. Think of it as a recipe for successful design. We start by setting up our environment, just like a chef preparing their kitchen. This means configuring our units, metric or imperial, and setting up our grid for precise work. Next comes creating geometry. This is where we draw our basic shapes like lines, circles, and arcs. Then we modify this geometry. Think of it as sculpting your design to perfection. Adding dimensions and annotations is like labeling your creation with all the important information others need to understand it. If we're working in 3D, we can transform our 2D sketches into three-dimensional models. It's like bringing our flat drawings to life. Then comes the crucial testing phase through simulation and analysis, and finally, we render our design for presentation or create manufacturing drawings. The applications of CADD are truly vast and exciting. In engineering, it's used across multiple disciplines. Mechanical engineers use it to design everything from tiny machine parts to complex tools and assemblies. Civil engineers rely on it for designing bridges, buildings, and planning entire cities. In architecture, CADD is invaluable for creating detailed floor plans, elevations, and bringing interior designs to life. In manufacturing, it's essential for creating precise molds and dies, and even generating the code for CNC machines. Product designers use it to create everything from consumer goods to medical devices. And here's something fascinating. CADD has even found its way into the entertainment industry, where it's used to create 3D models for animations and video games. Let's discuss why CADD has become indispensable in modern design and engineering. First, let's talk about enhanced productivity. Tasks that once took days can now be completed in hours. Imagine being able to copy, modify, and iterate designs instantly. The improvement in quality is remarkable. CAD's precision means fewer errors and more consistent results. Collaboration has been transformed. Teams can work together seamlessly, even from different locations across the globe. And the visualization capabilities are truly revolutionary. You can see exactly how your design will look and function before it's ever built. It's like having X-ray vision into your future product. This not only saves time and money, but also allows for better decision-making throughout the design process. Let's explore how we locate things in the CAD environment. Think of coordinate systems as the GPS of our digital design space. The most basic system we use is the Cartesian coordinate system. Imagine a map with an X and Y street grid. Every point in your design has a specific address, like 5, 3, meaning go 5 units right and 3 units up from our starting point. In 3D designs, we add a z-coordinate, like adding floors to a building. It's fascinating how this simple system allows us to place objects with perfect precision. Just like giving directions to a friend, these coordinates tell our CAD software exactly where we want each element of our design to be. Now, let's explore some more sophisticated ways of specifying locations in CAD. The polar coordinate system is particularly useful when working with circular designs or angles. Instead of saying go right and up, we say go this far at this angle, like a compass bearing and distance. For instance, point P, 30 degrees, means go 5 units at a 30-degree angle. Then we have relative coordinates, which are incredibly practical. They're like saying from where I am now, go 4 units right and 5 units up at 4, 5. The World Coordinate System, WCS, is our fixed reference frame. Think of it as our North Star that never moves. The User Coordinate System, UCS, is like having a movable compass that we can reorient to make complex designs easier to work with. Let's dive into the fundamental skills of 2D drafting. Imagine you're building with digital Legos, but instead of blocks, you're using lines, circles, and shapes to create precise technical drawings. When drawing lines, we start by selecting our line tool. It's like picking up a perfectly straight digital pencil. We can specify exactly where we want the line to start and end using our coordinate systems. Here's a practical tip. The orthogonal mode is like having a magical ruler that keeps your lines perfectly horizontal or vertical. And snapping? It's like having a magnetic force that pulls your cursor to exact points on the grid or to intersections with other objects. This ensures everything lines up perfectly. Now let's master the art of drawing circles in CAD. Unlike trying to draw a perfect circle by hand, CAD gives us several precise methods. The most common way is specifying a center point and radius. Imagine pushing a pin into paper and drawing around it with a compass, but with perfect precision. We can also define a circle using its diameter or by specifying 3 points that the circle must pass through. Think about drawing a circle through 3 fence posts. CAD calculates the perfect circle that touches all 3 points. For example, if we want a circle centered at point 3, 3 with a radius of 5 units, we simply input these values and voila, we have a mathematically perfect circle. Let's explore the fascinating world of drawing arcs. Think of them as pieces of a circle, like a rainbow or a curved bridge. In CAD, we have several methods to create these curved elements. We can define an arc by its starting point, center, and end point. Imagine drawing part of a circle but stopping at a specific point. Or we might specify the start and end points along with the radius, like defining how high and wide we want our rainbow to be. The 3-point method is particularly intuitive. It's like defining the path of a curved road by 3 points it must pass through. These tools give us incredible flexibility in creating smooth, curved elements in our designs, perfect for everything from mechanical parts to architectural features. Imagine you're creating a hexagonal bolt head or a pentagon-shaped garden design. CAD makes these complex shapes simple to create. When we draw polygons, we have several clever methods at our disposal. One approach is drawing the polygon inscribed within a circle. Picture placing a stop sign perfectly inside a circular frame. Another method is circumscribing the polygon around a circle, like wrapping a hexagonal frame around a circular pipe. The edge method is particularly intuitive. You simply define one side of the polygon, and CAD automatically completes the shape with all sides equal. For example, if we want to create a regular pentagon, we might specify its center at 0, 0 with a radius of 5 units, and CADD instantly generates all 5 sides with perfect symmetry. Let's explore the magical toolkit that makes CADD so powerful, our modification tools. Think of these as your digital sculpting tools, each serving a unique purpose. The Move tool is like picking up and relocating elements on your drawing, while Rotate spins objects around a point. Imagine turning a wheel. Scale is particularly fascinating. It's like having a digital magnifying glass that can make objects larger or smaller while maintaining their proportions. Trim is like having precise digital scissors, allowing you to remove unwanted parts of objects. Extend works in the opposite way. It's like stretching an element until it meets another object. Mirror creates perfect reflections of objects, essential for symmetrical designs. And Offset? It's like creating a parallel copy of an object at an exact distance, perfect for things like wall thicknesses or parallel paths. Let's explore how 2D drafting transforms various professional fields. In engineering, it's the foundation for creating precise technical drawings. Every bolt, gear, and component starts as a 2D drawing before becoming reality. Architects use it to craft detailed floor plans and elevations. Imagine being able to walk clients through their future home before it's built. In manufacturing, 2D drafting is crucial for creating flat patterns that will be cut or machined, like creating a precise template for cutting sheet metal. And in graphic design, it helps create clear, accurate schematic diagrams and blueprints. Each application demonstrates how 2D drafting bridges the gap between imagination and reality, turning ideas into precise, buildable plans. What makes 2D drafting in CADD so revolutionary? Let's break it down. First, there's the incredible speed. Tasks that once took hours with traditional drafting can now be completed in minutes. The precision is remarkable. Every line, angle, and dimension is mathematically perfect. The ease of use is a game changer. Modern CAD tools are intuitive enough for beginners, yet powerful enough for professionals. And perhaps most importantly, there's the interoperability. Your drawings can be shared and opened in various formats like DWG, DXF, or PDF, making collaboration seamless. It's like having a universal language for technical drawings that everyone in the industry can understand and use. Let's dive into one of the most crucial aspects of technical drawing, dimensioning. Think of dimensions as the recipe measurements for your design. They tell others exactly how to make what you've drawn. We have different types of dimensions for different needs. Linear dimensioning measures straight distances, like the length of a board or the width of a room. Angular dimensioning tells us about angles between elements, crucial for things like roof pitches or machine parts that need to rotate. Radial dimensioning helps us specify the size of curved features, like holes or rounded corners. Each type of dimension plays a vital role in communicating your design's exact specifications to others who will build or manufacture it. Let's explore more sophisticated dimensioning techniques that bring our technical drawings to life. Coordinate dimensioning is like creating a treasure map. It helps locate features using precise X and Y coordinates from a reference point. For example, when you need to specify the exact location of a hole on a metal plate, coordinate dimensioning tells the manufacturer, drill here, exactly 5 units right and 10 units up from the corner. Next, we have chamfer and fillet dimensioning, which deals with the softening of edges. Think of chamfers as beveled edges, like the edge of a diamond, while fillets are smooth, rounded corners, like the gentle curve where your desk meets its edge. Understanding how to properly indicate these features is crucial because they often serve important functional purposes, like preventing sharp edges or reducing stress concentrations in mechanical parts. Now, let's explore how we bring all our 2D tools together to create complete models. Think of 2D modeling as creating a detailed blueprint of your design. We start with our basic shapes, lines that form edges, circles for holes or curved features, arcs for partial curves, and polygons for more complex shapes. But here's where it gets interesting. We use geometric constraints to make sure everything stays exactly where we want it. It's like having invisible rules that say these lines must stay parallel or this circle must remain tangent to this line. The editing and modifying tools we discussed earlier become our digital sculpting tools, allowing us to trim excess material, extend lines to meet perfectly, create mirror images for symmetrical parts, and add those important fillets and chamfers that give our design its final polish. One of the most powerful features in 2D modeling is the layer system. Think of it as working with transparent sheets that you can stack on top of each other. Each layer can contain different elements of your drawing. One layer might hold all your dimension lines, another your main geometry, and yet another your annotation notes. The beauty of this system is that you can turn layers on and off like flicking switches, making it easier to focus on specific aspects of your design. For instance, when working on an electrical engineering project, you might have separate layers for circuit components, wiring diagrams, and dimension information. This organization makes complex drawings manageable and helps prevent different elements from visually interfering with each other. Let's discuss how modern CAD software revolutionizes our drawing practices. The interface is like having a smart workshop where every tool is perfectly organized and within reach. The dimensioning tools automate what used to be tedious manual work. Imagine having an assistant who can instantly add perfect dimensions to your drawing. Templates and standards are particularly valuable. They're like having pre-checked rulebooks that ensure your drawings comply with industry standards like ISO or ANSI. The symbol libraries are fantastic time savers. Instead of redrawing common symbols like weld marks or electrical components, you can simply insert them from a digital library. Custom blocks are another powerful feature. Think of them as creating your own reusable components. For example, if you frequently use a particular type of bolt in your designs, you can save it as a custom block and insert it whenever needed. Let's walk through the practical process of creating engineering drawings in CAD. We start with proper setup, like a chef preparing their kitchen before cooking. This includes setting our units, metric or imperial, defining our drawing scale, and organizing our layers. Then we move into the drawing creation phase, where we use our 2D tools to draft the basic shapes and apply geometric constraints to ensure accuracy. Dimensioning comes next, adding all the crucial measurements and annotations that will guide manufacturing. The editing phase is where we refine our drawing, making sure everything is precise and clear. Finally, in the finalization stage, we add finishing touches like hatching patterns to indicate materials and export our drawings in the appropriate format for our team or manufacturers to use. In our final slide, let's discuss how CAD fits into broader engineering practices. Following standard conventions is crucial. It's like speaking a universal language that all engineers understand. Different fields have their own specific standards. Mechanical engineers follow ISO 2768 for tolerances. Architects use ENSI/ASME 14.1 for layouts, and electrical engineers adhere to IEEE standards for circuit symbols. Modern CAD software supports cloud-based collaboration, allowing multiple team members to work on a project simultaneously. Imagine having engineers from different countries working together on the same design in real time. When it comes to documentation, CAD helps generate comprehensive bills of materials (BOM). Think of it as an automated shopping list of every component in your design. Finally, the software can produce detailed technical drawings that will guide manufacturing or construction teams in bringing your design to life. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.